Hi there, my name is Ken Bruton and I'm going to talk to you about the Digital Intelligence for Collaborative Energy Management and Manufacturing project, also known as DENiM, which we in UCC recently were a part of on the Horizon 2020 program. We operate in the energy management pillar of the MaREI Research Centre, where we do a lot of industrial energy management projects. So that's me, and I've worked in academia for the last number of years, but before that I worked in industry where I gained a lot of industrial energy efficiency experience right across Ireland and abroad. The aim of DENiM is to, I suppose, bring the current data that's available on an industrial site into the digital world so that we can start to make better decisions about how we utilise, consume and generate energy. There are 18 different partners all the way across Europe, but I suppose the cluster that we have is between UCC CIT and a local industrial site, DePuy Synthèse, who we have collaborated with for quite a while. The project is over 48 months with various milestones, but the two key ones that we'll be working on in UCC are fault detection diagnostics, energy simulation and optimization. There's an overall 11 million budget, of which UCC received funding allocation of just less than $500,000. So what will DENiM achieve? Today you have a lot of disparate sources of data on industrial sites for a lot of different reasons, primarily down to the legacy type of equipment which is on a lot of industrial sites throughout the world, and the fact that these aren't that easy to network and bring onto a live system. We hear a lot of talk about Industry 4.0, about connected equipment, but in reality it's quite difficult to tap into the huge quantity of data that's there. There's a lot of proprietary systems, there's a lot of off-grid systems. There's a lot of work to do in terms of getting an architecture there that we can take the information out and make better decisions on it. Energy efficiency is kind of independent of production processes. It's a byproduct. Obviously people want throughput, they want maximizing the amount of products they make, but energy efficiency is definitely seen as almost like a third or fourth in line after maybe labour costs and material costs in terms of where its importance lies. There's a lot of manual what-if analysis happening at the moment based on kind of heuristic knowledge built up over years and years and separated on key individuals. Planning is difficult in this kind of scenario where you don't have real-time information coming through to help you make better decisions, and there's a limited interaction with the grid in terms of trying to maximise the use of renewable energy while maximising your production output. And then lastly, there's a skills gap between subject matter expertise and maybe the data science side of it. So, a lot of times the companies are coming in saying, look, we'll solve your problems, give us all this data, we'll tell you what to do, but without specific knowledge of what the actual process is doing and how they're working in terms of the engineering mindset, it's difficult to line up the data with maybe effective decisions. So with DENiM, we hope to secure and maybe even get to a real-time data collection, aggregation and processing system whereby we're connecting to legacy equipment, we're getting over the data gaps that we currently have, we're starting to log information and keep it and make decisions based on it. There's a holistic approach to energy management, looking right across the industrial lifespan, where everything is connected. One impact is considered in the input into a different system. There's a continuous event-driven analysis, so we have accurate modelling of systems. They're not just operating and we don't really know what's happening with them. We maybe even have what we call a digital twin running next to it, where we have a simulation and a physical modelling running side by side, so one can optimise the other. We're constantly looking for inefficiencies and degradations, and we're making decisions around how to maintain and why to maintain at particular times, rather than doing it on a time basis. We're digitalising information that we currently have, maybe in paper basis or in people's heads, and we're pulling that into the information bucket so we can make better decisions based on that and other available data. And we're integrating renewables, so maybe even we're making more products when the wind is blowing more. Our industrial partner DePuy has 2 E101 Enercon turbines, they've got photovoltaic cells, they've got 2 biomass boilers, they've got 2 CHP systems. How are we using all of these systems? Are they optimal in their interoperation? And how are we going to bridge this gap between the data analysts and the system operators? They each need to understand a little bit about each other's world, and maybe we need people in the middle who understand a bit of both. So DENiM has a lot of objectives. We're going to try and map the energy flow across the complete manufacturing value chain. Tough. We're going to integrate energy efficiency into existing business processes through digitalization. It should be a decision-making point. We need to understand what's happening in an end-to-end way to do this. We're going to look for a significant reduction of energy across 4 different industrial sectors. We've got 4 different pilot sites in 4 different countries where we're going to look to show that the system works and it can be rolled out. Substantial cost savings of 15 to 20% based on optimized operation, and reduction in scrap and waste of 5 to 10%. So, not small targets in terms of what we're trying to achieve. And then a digital skills assessment so we can bridge this gap and hopefully maybe have new engineers who have a little bit of knowledge of the over, like if you think about the Venn diagram, that section in the middle, that's where we want the engineers of the future to exist. The skill set that we have and we're bringing to the project is very much in the energy performance modelling and simulation, and the interlinked field of fault detection, diagnostics and prognostics for energy efficiency, and then also in the integration of renewable energy into production processes. In terms of energy performance modelling and simulation, we're looking to develop generic support tools that we can use in different industrial paradigms. So look at reduced order modelling approaches like resistance capacitance models, RC models, because typically people don't use modelling a lot in industrial sites because there's rightly or wrongly a perception that the overhead is too big in terms of getting these models efficiently calibrated. So we're using Python to do RC models to try to use the data to drive the modelling process so we can be happy that the calibration is at a certain level which allows us to make decisions. Maybe we'll even get to the situation where the models running in parallel to the physical processes and the supporting processes, because it's not just the production we're looking at, we're also looking at the supporting utilities like compressed air, refrigeration, steam systems, low temperature hot water, DI water. And one of the really practical ways we can reduce consumption by using our modelling is by identifying periods where the systems aren't necessarily running at full pelt, where we could potentially put them into almost a lights out method where they're not fully turned off but they're idling at a lower energy consumption. So they're there to be used, but they're at the moment there's a lot of equipment running on 24/7 nature that doesn't need to be. In terms of fault detection diagnostics, our group, which I co-direct with Dr. Dominic O'Sullivan, the Intelligent Efficiency Research Group, has a lot of knowledge in the fault detection diagnostic space, and we've developed tools in heating, ventilation and air conditioning in the past, which we would hope to apply and extend to other utilities and to the process itself. But to do that we need to get the data out, which is typically the first stumbling block. We'd like to have intelligent agent-based systems on different systems that then interoperate together to make the best decision at the optimal time. And we'd like to extend it into machine learning, so we could potentially, like we use typically, first order models, regressive models. We want to get to prediction and prognostics where we're making decisions, where we're even maybe automating the decision process based on what the system feels is the correct forward-thinking option. And then looking to integrate renewable energy into the production process. Could we make more parts when the wind is blowing? Could we potentially alter the production planning process to be more efficient in how it's operated, or to even take energy into account in how it's put together? There's 2 auto-generating wind turbines. They spill a little, not a lot at the moment, but could we potentially eliminate that spill and consume it all on site in a more efficient way, thereby not putting the problem of the intermittent use into the grid? And could we maybe use more renewable energy when it's on the grid by maximising our use of it in a production planning method again? So the work packages are wide and varied. From 1 to 4, there's very much a framework and an architecture, and from 7 to 9, we're talking about how to implement and evaluate and exploit and disseminate. From our perspective in UCC, we're very much in the 5 and 6, which are about holistic modelling and continuous performance assessment and sustainable driven decision support tools. So building on what we know, so we can develop reduced capacitance or resistance capacitance, reduced order models to try to optimize systems, to understand them first and then to optimize them, and to try and give people the data they need to make better decisions. And then moving on in terms of decision support, how do we operate fault detection systems so we can maybe help the facilities and the maintenance department make better decisions about when they maintain their plant? Could we identify degradation before it happens? Could we save assets from going into a fallen state when they could be making products, and we could be using renewable energy at a particular point in time? So that's the DENiM project. It's pretty wide-ranging, but it builds on our expertise, which is industrial energy efficiency, performance modelling, fault detection diagnostics, digitization, and integrating with the smart grid. Thanks for listening.